Okay, so this is section 6.2 from MA 259, and question number 3. Our directions tell us to discuss what's happening at the critical point 0, 0 using theorem 1. And theorem 1 is just the chart that we've already talked about in the past. So let's walk through this problem. So what I do is they've already told us what the critical point is at 0, 0. And so we are trying to figure out then what our eigenvalues are. So I make my a minus lambda I, take its determinant and set it equal to 0. So I have 1, 2, and then 2, 1 for my a, and then minus lambda I, and then take its determinant. And when I do that, I end up getting lambda equals -1 or 3. So lambda equals -1 or lambda equals to 3. And so we have real, unequal, and opposite signs. And when I look at my other table, real, unequal, opposite signs, that tells me I have a saddle point. And so really we've solved that problem. But if I look at the other chart, I can get a little bit more information. Now again, our actual directions doesn't tell us to look at the other chart, but let's do that anyways. Lambda 1 is less than 0 and lambda 2 is bigger than 0. And so when I look at that, I get lambda 1 is less than 0 and lambda 2 is bigger than 0, and it tells us that I have an unstable saddle point. Okay, let's look at the next problem, number 12. All right, so number 12 asks us to classify the critical points, and in this case, we're responsible for figuring out what the critical points are. So I recopied the problem, and then I set each of the differential equations equal to 0. So x minus 2y minus a equals 0, and that comes from the first differential equation. And then the second differential equation is x plus 4y plus 10, and I set that equal to 0. And then I end up getting the system, the linear system as it turns out, of x minus 2y equals 8. So I move this -8 over to the other side. And x plus 4y equals -10. So I took this positive 10 and moved it over to the other side. And I put that into a augmented matrix and put that redo row echelon form, and it tells me that x is equal to 2 and y is equal to -3. So I have a critical point at x comma y, which is 2, -3. Okay, so there are a couple of techniques that our book talks about, but we might as well go for the home run hitter every time. And so we are going to find the Jacobian of our a differential equation and form this Jacobian A matrix. So what I do is take the partial derivative with respect to x of my first equation, and then my partial derivative with respect to y of my first equation. And then I take the partial derivative with respect to x of the second equation, and the partial derivative with respect to y of the second equation. So the partial derivative with respect to x of the first equation, that would be 1. So I write a 1 here. Then I write the partial derivative with respect to y of that first equation. So that's -2. So I write a -2. Then the partial derivative with respect to x of the second equation would be 1. So I write a 1. And the partial derivative with respect to y of the second equation would be 4. So I write a 4. So I have this Jacobian matrix of 1, -2, 1, 4. Then I evaluate this Jacobian matrix at the critical point 2, -3, and I get, well, I get the same thing, 1, -2, 1, 4. So then this forms my new A, and so this is a minus lambda I, take its derivative, or not derivative, sorry, a minus lambda I, take its determinant, set it equal to 0, and I get 1 minus lambda, -2, 1, 4 minus lambda, take its determinant, set it equal to 0. So I found the determinant, and when I solve that, I get lambda equals 3 and lambda equals to 2. So this is the case when lambda 1 is bigger than lambda 2, but they're both positive. So I look at my chart, and I have lambda 1 is bigger than lambda 2, but they're both positive. And so that is an unstable improper node. So unstable improper node, and that's happening at 2, -3.